Our second example is a extension of the permutation test for two samples. And this example is a test for the correlation on paired data. The permutation test can be adapted to paired data. For instance, to test for the multivariate independence. In this case, our null hypothesis is that the joint distribution is equal to the product of the marginals, x and y, if we're interested in whether x and y are independent. So this is the general hypothesis. You can see that intuitively under H0, the null hypothesis, where the two are independent, the conditional distribution of y given x should be the same as the marginal distribution of y. So the distribution of y shouldn't depend on x. In other words, if we keep x's fixed, in other words, unshuffled, we may permute our y's, and the resulting samples, xy's, are equally likely. We will see a concrete example based on the punting data inside the faraway package. So here's an introduction to the dataset. The dataset called punting involves the physical characteristics and punting ability of 13 American football players. So investigators studied physical characteristics and ability of 13 football punters. Each volunteer punted a football 10 times. The investigators recorded the average distance for the 10 punts in feet. If you want to look at the documentations, you can look at the help file, so question mark punting, to be able to see all of the descriptions of this data set. Here, I am just printing the first few rows of this data frame. So you can see that the data frame contains multiple columns, but the two we will look at is the distance column, which corresponds to the average distance for the 10 punts, and the RSTR column, which is their right leg strength. We'll examine the relationship between right leg strength, RSTR, and punting distance. It's called distance. And we will test the hypothesis, where the null hypothesis is that these two are uncorrelated, so rho equals 0. And the alternative hypothesis, H1, is that they have a positive correlation. So you can see we're doing a one-sided test here. Our test statistic, theta hat, is going to be the Pearson correlation between x and y, or the Pearson correlation between unpermuted or permuted x and y's. So here we have the code for creating our x and y's, where x is the RSTR column of punting and y is the distance column. But before we look at the rows, let's first look at a scatter plot. Here's a scatter plot of x and y, and they appear to be correlated. So we can perform the permutation test by keeping x unpermuted and permute the y's. Again, if there is truly no association of leg strength and punting distance, then the distribution of xi with y pi I, so permuted y's, should be the same as that of xi and yi. Here, pi I is again the ith element of the permutation pi applied to 1, 2, all the way up to 13. Since we are no longer doing a two-sample test comparing the distribution difference between two groups, we do not need to do unique partitions. In this case, instead of counting the number of unique partitions, we will count the total number of possible permutations. So total number of possible ways that we can shuffle our y's. And that's given by 13 factorial. You can see that this is something that is really large. So it looks like we will need to use Monte Carlo approximation again. So let's again use B equals 999. Our first step is still to compute theta hat. which is the Pearson correlation between the original x and original y. And then we can obtain the theta hat j's, which is theta hat computed from the shuffled or the permuted samples. We use the replicate function and replicate this for a total of b times. Each time we permute our y's, we shuffle our y's, and this can be done by sampling with replacement a total of 13 elements from y, without replacement, sorry. And then after we permute our y's, we can again calculate the correlation between x and the permuted y's. These are going to be our theta hat j's. So at the end, we again calculate the p-value. This is given by the mean that the concatenation of theta hat and the permuted theta hat j's, a total of 1000 here, is larger than or equal to the observed theta hat computed with the unpermuted sample. And we get a p-value of 0.001. So if we use a alpha level of 0.05, then this is something that's highly significant. So given that under the null hypothesis that x and y are uncorrelated, there is only around 0.1% chance that we observe a theta hat that's larger than or equal to what we have from the observed sample. So in other words, in this case, we reject the null hypothesis, and we can conclude that x and y don't seem to be independent. Let's compare this to the result for a t-test for non-zero correlations. So this can be done using the core.test function in R. So you only need to supply the core.x and y, and then the alternative hypothesis is greater, meaning that we will look at the alternative hypothesis that rho is greater than 0. And here are the results we get. We can see that the p-value over here is something around 0.0006, which is also very small. And the observed sample Pearson correlation between x and y is actually around 0.79. So it's a very strong correlation. In other words, we can see that the permutation test and the Pearson's product moment correlation test of non-zero correlation give us the same conclusion of rejecting the null hypothesis that x and y are independent.